Okay, so this is the second of my lectures on algebraic surgery. And this one will again start with geometric surgery. So let me remind myself. So geometric surgery on an n-dimensional manifold requires two things: an embedded sphere and through an extension of the embedding to SR cross. Okay, so you have a framed embedded sphere. Then the effect of the surgery is, as always, N prime. Remove the framed embedding and replace it by the dual sphere. So that's easy. So I want to talk, this is an algebraic surgery lecture, on how to translate these kind of things into purely algebraic conditions, which in favorable cases the algebra and the geometry match. So there'll be an embedded sphere if and only if, well, there's an embedded sphere in the algebra, and there's such an extension if and only if there's such an extension in the geometry. But of course, this is very far away from geometry. Just as a manifold is, of course, a very geometric topological thing. So embedded spheres and these spheres of this are also pretty geometric. So it's not quite so trivial. So where do 1 and 2 come from in topology? So 1 from Hurewicz and Whitney. So the Hurewicz theorem says that if, well, let's say first that if pi rx, pi rm, pi kn is 0, that's not a special case, because in general one doesn't want to assume, in general it's not possible, as I'll explain, to get this inductive hypothesis going very much. If you take a manifold, it's very unlikely that you can kill already the first fundamental, the homotopy group in any kind of sensible way. Well, you can actually do that, but the second one gets to be a problem. So, but this is a model. So this is the Hurewicz isomorphism. And the point here is, in the kind of baby way, you see that every element in the homology group, homology is something which is very algebraic. So what I was doing last time was talking about how you get a chain complex with symmetric Poincare duality from any manifold or any space with Poincare duality. So certainly, this can be algebraicized very easily. What you don't know in general is whether if you have some homology class, whether it's represented by a map from a sphere. So in this case you do. So every x is represented by a map, at least. And then what Whitney does, assuming n is big, which always means greater than 4, and 2r is less than m, can represent x by an embedding. So this is, let's with this embedding theorem. Okay, so these are going to be the ingredients also in the more general case of trying to do surgery on not just on a manifold, which is in general not possible, but on a normal map, which is in general possible below the middle dimension. Okay, so that's kind of the ingredients. The other thing that one needs, of course, is a normal bundle. So there one really needs to know about the work of Whitehead and Steenrod, and Hopf, I suppose, and also Whitney. All these people from the late 30s were so active. And this is to do with the normal bundle. The SR has a normal bundle. Which I'll just write using the standard terminology for classifying spaces. So you have a map from an R sphere to BO n minus R, the classifying space for n minus R plane bundles. And in order to do surgery, we need this nu to be non-homotopic or bundle to be trivial. To extend, so the problem was to extend this, from the thing given by with the embedding theorem to an actual is the same, an extension maybe, an extension from this is the same as a trivialization of the normal n minus R plane bundle nu. And so that looks like a kind of unstable homotopy problem. If and only this classifying map is not homotopic. So that's pretty bad in one sense, but it's not very algebraic, I mean by bad. But if, at least in this, you already have to assume that 2r is less than n in order to get the, be able to apply the Courage theorem and all this kind of stuff. So if 2r less than n, nu the homotopy classes of this are in one-to-one correspondence with the stable homotopy groups. So that's quite good, because by the Bott-Realistic theorem, one actually knows relatively well, in fact very well, what these are relatively small, Z or Z2. However, it's slightly illusory in that the kind of invariance, explicit invariance here you get, are not very susceptible to chain methods. They depend on homotopy theory. It's a very non-trivial theorem in homotopy theory, and here, for example, you have the Chern class or Pontryagin class with some even more exotic invariance. So I thought this looks relatively easy. It's not chain, it's not homological. At any rate, but it's quite useful. But we can concentrate on the fact, so don't need an actual trivialization, so an isomorphism of the trivial bundle, it suffices to have nu plus epsilon k. So that was a big idea which kind of first really became prominence with exotic spheres, with such application, so stable spiralizations. And then there were all these people studying this kind of question. So that's kind of the philosophy that you get, at least which works fine below the dimension. You can apply all this work and reduce it to, in some senses, well, computable things. But what's really missing here is some systematic way of proceeding. I mean, it's not, since it's in general, I'll give an example now, it's just not possible to work your way up to kill the higher homotopy groups. The standard example, there's an example in the oriented case and the same example in the non-oriented case. So, we may have mentioned it last time, I can't remember. I mentioned it again. It cannot be mentioned often enough. It's so crucial. Now, done is over here. Okay, so why isn't that enough? In general, cannot kill pi star m by surgery. Okay, so because the cobordism groups, because cobordism equals surgery. I hope I mentioned that last time. And cobordism groups are non-zero. So asking to kill all the homotopy groups by surgery is pretty bad. However, I'm simply because of the cobordism thing. And standard example in, so RP2, not cobordant, not null cobordant. So you take the generator, let's call this RP1, which is S1 in RP2. So that's a perfectly good embedding. RP1 and RP2 has even stably non-trivial normal bundle. Okay, in fact, well, this is, because this is PO1 is RP infinity. Well, just look at the fact that this is RP infinity, that's a good way. And pi 1 is the generator of not equal to 1 of pi 1. The first Stiefel-Whitney class will do it. It's not orientable, and that's a nice stable invariant. This is nu. Okay, so that's one very complicated proof that RP2 is not cobordant to the, not non-cobordant. Or this is non-orientable, of course. And this line band, this is the Möbius band, of course. And similarly, if you want not oriented, not non-cobordant. So the correct way to do it, of course, is to simply say, well, the signature of CP2 is 1, and signature is a cobordism invariant. But I would like to also go through the same thing. Again, you have an embedding, CP2, of S2 in CP2, and then nu this is now a more interesting invariant, oops, because this now lives in BSO2, which is CP infinity, and it's so has non-trivial. So this was, previously was non-trivial W1. This has non-trivial first Chen class. So this was Stiefel-Whitney. So the characteristic classes are perfectly good abstractions to normal bundles being trivial. They're abstractions to any bundle being trivial, but in particular normal bundles. And these are the standard examples of. So you can see, even already on the level of surgeries, let alone on the level of cobordism groups, that it's going to be quite difficult to work your way up. If you're going to try to do surgery in all dimensions as much as possible, these kind of low-dimensional examples show this is a somewhat hazardous enterprise full of obstructions already here. Nevertheless, ever since Keller and Milner, there's been a whole program for working with not on a manifold, trying to completely destroy the manifold by surgery. This cannot be done, but to try to decide whether a manifold is homotopy equivalent to another space, which doesn't in general have to be, if it's contractible, that's kind of hopeless. So there's a kind of mechanism here. And mechanism is known as normal maps. So this was first invented by Milner in a very special case, actually a very general case, but then until he got off the ground with the work of Browder and Novikov and Salvin and Wall. So what I want to do now is to introduce the concept of a normal map, and try to explain why it's useful for geometric surgery, and then how to translate it into algebra. And for normal maps, unlike for absolute manifolds, things look up. So let's have normal maps. This slide. This doesn't look a very grammatical sentence, but the army, British Army at least, had a huge list of objects. They were always making lists of things, because whenever they moved from one place to another, they needed all the equipment. And they had a long, kind of special way of writing things down. So they would, you would look up at the normal maps, surgery on, for the use of, because everything was very backwards. So this is similarly here, surgery on. So this is like, before I was trying to do, I failed to do surgery on manifolds, now I'm trying to do surgery on normal maps. So the definition is much more general than is normally, so to speak, accepted. A normal map looks like this. From an n-dimensional manifold M, so that's very good. Together with the actual map, a vector bundle. This is all. Let's all work in a smooth category. A vector bundle, a stable vector bundle, K is large, and the bundle map. So that was one of the many things introduced, not so much by the generation of Whitehead and Steno and Hoppe, a little later by, I think especially Milner involved. These people stable. So this is that B here refers to that. Okay, so there's a vector bundle over here. This is an embedding. For K large, there's an essentially unique embedding of a manifold sphere. So why is that a good thing? Well, because now we'll apply these techniques not to the absolute groups of M, homotopy groups, but to the relative homotopy groups of F. I think you know already. So, and that will work, at least below the middle dimension, and at least But first let me just give it. Now, one question is, where do normal maps come from? There's one, the original normal map, which was defined by Milner in 1960, wasn't, this one's not familiar with the kind of yoga of having degree 1 map from a manifold to a Poincare complex and all that. It come a little later. In fact, did come a little later. Original example. Milner, this is a paper of his called A Procedure for Killing the Homotopy Groups of Manifolds. All right. Take any manifold, take X, and F is a classifying map. It's a perfectly good example of a normal map, where here you've got exactly that normal time. And here you take the universal, well, so it's the principal bundle, a contractible space with a free action of OK, and then, well, some kind of fantastic ways of getting, in fact, to be precise. I think you can do this. That's the actual definition. At any rate, there's a canonical map if you take the universal. This is the universal K. And now things are easier, because instead of trying to make M null coordinate by surgeries, already it is not possible already for RP2, CP2, already, okay, so that's hopeless. Try to make F as close to a homotopy equivalence as possible. Well, as possible. By surgeries on M, keeping X fixed. So it's not a moving target, it's a fixed target. So, well, this is also going to be impossible for this particular X, because, well, this is a space which doesn't have Poincare duality. It cannot be homotopy equivalent to a space which has Poincare duality. This is a space which is infinite dimensional in every possible way. This is a space which is finite dimensional in a very precise way. So that wasn't quite fair. Nevertheless, he had a theorem there which said at least below the middle dimension you can do things. Okay, so provided you're careful and use the fact that the homotopy groups of BO, okay, large after all, are finite generated, you can do something below the middle dimension. Or at least are connected for 2r less than n. That could be done. And now, a little later, this was Milner 1960, there was a whole kind of thing of, I mentioned Browder and so on, where you took X not to be BOK, but to be a Poincare duality space. And then, instead of starting with a manifold and trying to decide, for no particular reason, how close it is to BOK, you started off, or they started off, with a Poincare complex and asked, does there exist a manifold with a normal map? And the problem became, when is a space with Poincare duality homotopy equivalent to a manifold? Standard problem. So
if you want to translate it back to the original problem that you know you can't solve, do you take X just to be a sphere of the right dimension?
Yes, you could. I mean, the problem is that every manifold has a degree 1 map from it to a sphere. But in general, it will not be a normal map. So in order to apply both these things, so you need some kind of a So, well, let me just do a little bit of trying to explain surgeon manifolds or normal maps. But the idea is the same as here, except now one's going to be looking not at the absolute molecules of M, but the relative molecules of F. And then below the middle dimension, these kind of arguments will give work. And what is more, it will be relatively possible. You won't have this characteristic class abstractions, because you will only be trying to kill the difference between M and X, not M itself. And that's much more feasible. So that's the kind of difference from the in the 1950s you would try, or the people did try to compute, succeed in computing cobolism groups. So the question was, so they didn't use surgery methods directly. The question was, can you make a manifold coordinate to the empty set? Here you try the same methods, so to speak, surgery methods, to decide whether a manifold is closer to being X than it already is. Right? And how close to X can you make it by surgeries? Of course, X could, for a framed manifold, this definition, so that's one example. Another example, even earlier, goes back to Pontryagin. Take M to be a framed manifold. That means that the normal bundle is trivial or trivialized. And then you would regard, from the modern point of view, as a normal map from M to a point. And then you can try the question of whether this normal map is broadened or can be done by, reduced by surgery to homotopy equivalence, is framed cobordism. This is, well, but some of this is, so modern, I mean, still was very influential, and surgery theory still feeds off the Pontryagin isomorphism between framed cobordism and stable homotopy groups of spheres. Okay, let's straight a bit. So let me try to, so in particular, all this is still not very algebraic. So it came on in the late 60s that these kind of questions become susceptible to crude algebraic treatment. Okay, so before let me now switch to algebra a bit and try to explain, before I do normal maps from manifolds from Poincare complexes, how one translates, how one sees normal bundles in algebra. So it's not obvious. See, because what I did last time, so in anticipation of geometric and algebraic surgery in key cases, I need to just describe how one wants to just pass from geometry to algebra, generalizing. Well, so we had one manifold, Poincare duality space. M. So what I had last time was Cm was some kind of chain complex. For simplicity, they just work over Z. I mean, the full theory uses fundamental group, but it's kind of stuff complicated. So just think. And then phi was all these businesses. Where you have these structure equations. Phi minus 1 is 0. And so in particular, phi naught was the Poincare duality chain equivalence. Phi 1 chain homotopy from phi naught to phi naught star. Phi s in general, s plus 1, just like here. This equation means that phi s is a chain homotopy from phi s minus 1 to phi s minus 1 star. Not very well written. Okay. So it's a sequence of, well, the things which come from the Alexander Steenrod-Whitney, or maybe Alexander-Whitney Steenrod diagonal chain approximations. And so in general, there is this natural transformation for any space M, and it's very natural. It's very hard to get an explicit description. So it's kind of was done for some additional complexes by Steenrod. Invented the whole business. There exists a natural diagonal chain approximation. The problem with getting it going is that it requires something which is somewhat out of date now, acyclic models. I mean, experts know about it, but I think it's slightly forgotten. It comes from the fact that the Eilenberg-Silber theorem tells you that this chain complex is chain equivalent to that chain complex. And there are two, let's take singular chains for simplicity. There are two ways of defining a Z2 action. You can either do it geometrically, Tx, Y is Yx, or you can define it here algebraically, Ta tensor B. Unfortunately, they don't quite match up. There is a chain equivalence either way, but the chain equivalence is not Z2 equivariant. It's only Z2 equivariant up to chain homotopy. So that's very serious. And this chain homotopy is itself chain homotopic to something by an EZ2, and so on and so on and so on, exactly as this. So this W, I should say, is the standard free ZZ2 resolution So a chain map here is exactly consists of all these, delta ms is Cm. So there's a natural map. So what's easy is to define a map from here to here, because there's a geometric map, the diagonal. The actual diagonal is perfectly okay. And then you need all this acyclic model stuff, the Silber theorem, to relate this to that with all the higher ones. So this is the definition of delta ms. And I'm going a bit quickly here, but that's the way it is. So that's a very functorial thing. Like that's what you can write down for any chain theory, particularly singular chains, these natural transformations. And if you have a map of spaces, for example, F, N to N, it has all the nice features. This diagram commutes. And this phi here is nothing but this diagonal, extended diagonal map, evaluated on the fundamental class, or fundamental Okay, so it's a very general construction. I'm not using at all the fact it's a manifold. I'm only using the fact it's space with a homology class.
So
Yeah.
this EZS isn't a chain homotopy between...
No, it's a higher. You have exactly the same rules. D, E, Z, S.
I'm just asking because you've written a homotopy between...
Yeah, I have to. It just means, the actual chain homotopy is here.
Yeah, right.
These are, no, but there are these higher ones, like this.
Yeah.
Okay. Something like that. So this is not at all close to vector bundles. Right? It just says for all spaces with a homology class, you can write down a chain complex with this chain map. So in general, I'm not even assuming that this is a chain equivalence. All I'm saying is, whenever I have a space M with a homology class, I have this kind of structure, which I would call an n-dimensional symmetric complex. Of course, if this is a fundamental class of a manifold, then you have the extra structure, this is a chain equivalence. But that's not somehow what... And I should perhaps explain what is the name of the key properties of these higher phis. They are the Steno squares. So every space, that was the Steno comes in, or came in, oops. So there are the specific Z2 coefficients. What you do is you take a So here you put in, they call it delta M, n minus 2r. And then you put here C tensor C, and then you've got Z2. So that's the definition of the Steno squares. And what we want, rather strangely, in the situation that's not, I'm not using anything here other than chosen n minus r and n for a good reason. It's that in this situation, where you have a preferred homology class, rather unobviously, this composite has something to do with the normal bundle. So now I'm going to tie in what I had earlier. So if M is a manifold, it's an N manifold, it doesn't have to be oriented particularly with fundamental class. The composite, this composite, depends only on the normal bundle. Depends only on the normal bundle. So now this is not so obvious. I mean, it has been known for 60 years, but it is in fact, it is dual, besides here. It is in fact call it? The V class. So there's some characteristic class called the V class of that normal bundle. And this other strangely should have been R, of course. What have we got? Yeah. So this is Poincare duality. Okay, so this is the two coefficients, and this is exactly that, because this is isomorphic to this by the universal coefficient theorem. So this is a very interesting relationship, first obtained by Wu and Tom, and this is the theorem of Wu and Tom, really. And this is going to be the way in which we'll translate the vector bundle information into homological information. So it's not entirely clear why this has something to do with that. Nor have I actually defined it yet, the Wu class. So, what's a good way of defining the Wu class of any vector bundle or spherical fibration? In fact, this depends only on the spherical, in fact, well, of spherical fibration. I won't go to. It's enough to know that there's a vector bundle here for a Wu class for a vector bundle. Okay, so now we have a problem, which is how do I express this as yet here undefined characteristic class. So it's a very weak characteristic class. In fact, it's related to the Stiefel-Whitney classes rather than anything like the Chen class. There's only mod 2. And yet it has in it kind of the seeds of the way in which normal map information over is translated into algebra. So the point being that there will be some kind of relationship, not just between the manifold and its normal bundle, but trivializations of the normal bundle, perhaps only on the part of the manifold, to quadratic structures. So that's kind of important. There should be some kind of the motivation for this is, again, not just to kill the homotopy or the homology groups of the manifold, but of all of it, but part of it. So that's where this normal map comes in. So let me just, before I get stuck into these Wu classes, try to explain what's going on. So I mentioned the Pontryagin-Thom theorem, which says that frame manifolds are coordinate, the frame coordinates the same state of homology groups of spheres. So if we now go back to this slightly earlier, going back a few blackboards, a framed N manifold so that's a pair of a manifold and a realization of the normal bundle of the manifold of the sphere. A Riemann manifold is the same as a normal map where X, the target, is a point. Because there's only one vector bundle over X, in which dimension the Tirol bundle, and pulling it back for large K, it gives the same as a framing. Can, in fact, kill pi Rm for 2r less than n by surgery below the middle dimension. So that's by the case using the Horevich theorem and all this kind of thing. So that's the one case where you can actually do this here it is that record 2 as on 2 above. The way to generalize this is to say, well, if X is a more complicated space than a point, you want to be able to kill the difference between M and X, at least below the dimension. So we'll want to, in general, given a more general normal map, will be able, at least in favorable cases, but in many favorable cases, to do the same. Would be able to do the same, i.e. kill, i.e. make F out, but killing what I would call pi RF. So that's the, okay, that's the thing which, maybe I should call it pi R plus 1F. The thing which sits in the exact sequence, right, below the middle dimension for 2R less than N. Now, what does this have to do with anything? Well, the point being that somehow this kind of connection, which I haven't really established, but simply said that this is all to do with C0 squares, will apply not to all of them on the level algebra. It's very hard to kind of look at the homomorphic groups algebraically. But if you are in luck, there is a Hurewicz map, and there's always a Hurewicz map, paired lattice and isomorphism. And the point being that over here, this relative homology group behaves like a frame manifold in algebra. Like a frame manifold in algebra. There's just enough space, well, not just really enough, in algebra. So the motivation for trying to understand the connection between a manifold and its normal bundle on the level of Wu classes is that in a general situation, there will be a map from a manifold to some space, which is a bundle map. That's very important. And if you look at the difference between M and X, the relative homomorphic groups, well, there, all the kind of vector bundle information conspires to tell you it's trivial over here. Because, like, when you're looking at normal, if you had an embedding, say, you would have that the normal bundle is stably trivial on account of F and B. Right? So, I mean, maybe I should do good to kind of expand on this a little bit. But the idea is that in the general situation where X is not just a point, it still somehow behaves on the kernel difference algebraically like a frame manifold. And particularly this connection between, it's what looks like a relatively weak connection between the normal bundle and algebraic information or chronological information turns out to be okay, because if you're in the Hurewicz dimension, this is the same as that. And then the quadratic information which you need, or the kind of reasons for having a normal bundle, trivial, which come from this translation, are enough to get you through. So it's a program rather than a result. Okay, so clearly I'll stop in about 15 minutes and carry on next week. Sorry about that. So let me try to, I think, motivated why I want to have this connection. Let me try to explain how does one see this. It's very unobvious. And what's unobvious is that I would like to have an algebraic way, not just of understanding C0 squares, this I've done. That's what I already kind of explained, that any space M has a diagonal chain map, and you're very happy to see that the C0 squares are built in. I don't know, probably somewhere way out over there. Okay. The spherical fibration of vector bundles was another great idea of Tom's, which is that you should look at the Tom space. Okay, but the Tom space doesn't have a homology class. There's a cohomology class, the Tom class. So to get chain of homological invariance of vector bundles, you have to look at spaces not with a homology class, That was a cohomology class. And a great theorem of Attias and Walls and other people too says that in the case of a manifold of Poincare duality space with a normal bundle of this without normal fibration, the Thom space of that normal bundle is S-dual to the manifold itself. So this would connect up. So this would be the connection which actually goes back a little bit, a lot, to Thom. Will tell us not only how to translate vector bundle information to homology, but in the situation of where the normal bundle is, where the bundle is a normal bundle, why it relates to this T0 squares. So I've got quite a lot to do in the next 10 minutes. So this is not a complete translation in the sense that it's going to lose. It's not going to say anything about contrarian classes, for example. It's just a question of group classes. But it turns out that this is adequate for the kind of quadratic information you need for surgery theory, because it actually also generalizes not so much to the contrarian classes and things like that, but to the universal cover, if you do it right. Okay, so 9, 10, 11. Now we're doing the section. How does a vector bundle, eta, let's call this space, that's some space X, or so in fact sphere bundle or spherical fibration, translate into cohomology? Well, I'll make life very simple for myself by working with mod 2 coefficients. So I don't just, and the answer is, use the Thom space. And the Thom class. In the oriented case, you don't need, you can work with integer coefficients. In Z coefficients in general, with Z in oriented case. Okay, so the way to define, let's assume it's a vector bundle. So look at this kind of thing. The Thom space from this point of view is just the one-point multiplication of the total space. So that's easy. For example, if X were a point and this was a trivial K-plane bundle over a point, this would be the identity. And in this case, it's just the case here. And the obvious class to take would be 1 in the kth, reduced kth homology, which is just, of course, Z2. So it's not very sophisticated what you do in this case. But it turns out that it actually works in general, because the characterization of the Thom class is that, continue with that. So there's a, working with mod 2 coefficients, it's a unique class which on each point here, let's restricts to this. The pullback of any vector bundle to a point is a trivial bundle. So so this U, I just want it to be sent to this element for each inclusion. So it's a very nice, it's like the fundamental class of a manifold, which I didn't discuss. So it's like a fundamental co-class of a vector bundle. Okay, but it's not good enough to translate into algebra directly because we don't have a homology class. I mean, the whole construction of that phi used the homology class. Well, there's a very nice theorem mentioned already. I want to stop that. I want to stop it. I want to bring it down. Up. So the theorem says that for any space Y, there's another space Z whose cohomology is the homology. So the S-duality theorem, I'll use pointed spaces, S-duality theorem. And I suppose the person to whom deserves most credit is the late Spanier. If X, or rather if Y is a pointed space, pointed finite CW complex, that generalization is to other spaces, but this is the easiest one. And N is a large number. It's sufficiently large compared to the dimensions, say, e.g. Y is in Sn, so there's a theorem which says that every finite simplicial complex, every finite CW complex, can be embedded up to homotopy equivalence in some high-dimensional Euclidean space. There exists a pointed finite CW complex Z Okay, so it's a very surprising thing. The cohomology of a space is the homology of another space. So it's very familiar from Alexander duality, and, well, also from manifolds. And proof given Y let be a regular neighborhood. There are various versions of this theorem, and Spanier's original version was in fact to look at Z to be Sn minus Y, and then there's a map like that, but it's not somewhat artificial, it uses linking numbers and so on, and it doesn't generalize very well to non-simple in this case, but that's one possibility. I prefer this possibility, but it does require Whitehead's theorem of theory of regular neighborhoods in Sn. So in particular, that is a projection map. It's like a normal bundle of a manifold. Every time you have a finite subcomplex of Sn, of any manifold, you can look at second derived neighborhoods, and you can get a nice tubular neighborhood, so to speak, except it's not a cube. But this is a homotopy equivalence, in fact, a simple homotopy equivalence. And then you look at the following from Geiger-Tom construction. You take Sn, you collapse everything outside of W to a point. That's given by that. And then you take this. And then you have almost what's wanted. So this is really not entirely fair because it's going to be the homology Y plus. It's not, and it's only something in the dimension, in the bottom dimension. Okay, so this composite is described in Tomma, has the property that, and this is somewhat of equivalent to Y plus Z, where Z is okay. So these are related by exactly this theorem that the homology of Y, which is a reduced homology of Y plus is Y union a point, is isomorphic to the cohomology, or rather homology of Z. So, and it's given by the adjoint of this composite. If you look at what it does, it tells you there's a homology class, and it's a cut product. Let's call this cut product with delta. Let's call this delta, or, well, let's just call it delta. So cut product with this particular delta, which is essentially the diagonal, tells me that, or tells us, that the cohomology of Y is the homology of Z, where Z is this. So what if Y were manifold? Then this would be exactly the definition of the normal bundle of the embedding of the manifold in the sphere, and this would be the Thom space. If Y is a manifold. If Y is a manifold. And what this is telling us is that for a manifold at least, the manifold plus a base point is S-dual to the Thom space. So next time I'll talk about how to use the Thom space to get invariance of a vector bundle.